So here is Barbara from Riversdale, South Africa, somebody from San Diego, part of the Soil Food Web School. Lucy is in Kenya and Njoro. Jessie is on a small farm in Ontario. Ireland, Kenya, very nice. Somebody's got your books. They got me into Elaine's courses. Katie, wonderful. She's in Canada. Elizabeth Mangara, that's one of my students. There's another of my students. Keep me muted. I'm all about chaos. Okay, so hello, everybody. Thank you for joining this webinar. I really like the turnout that's growing. What fun it is to have so many folk passionate about soil microbes all in one place. We've got farmers, gardeners, soil scientists, soil advocates. Big love to all of my students out there. We've got researchers, Soil Food Web Lab technicians and Soil Food Web Lab students. Big love to the African Soil Food Web fraternity. Thank you for joining. And we've got consumers here with us today. I love the idea that our common bond and interest are the little guys that power our world day and night. And thank you all for caring. So a little heads up about some housekeeping. Two things really. One, go wild on the emojis. There's nothing better than giving a presentation than to feel the love from one's audience through emojis or emotions. Even if you're sad, if you're happy, if you're surprised, hit the emoji button whenever you feel like it, because that helps us all stay connected. And then two, at the end of the hour, we'll be taking a question and answer session. So if you have any questions, send them to me on the chat, directly to me. My name for the evening is Q&A host. And then I will go through your questions and I'll bring them up with Jeff at the end. And if we have time, we'll also unmute some of the microphones and you can speak with him. Whilst on the topic of names, I'm Su Kahumbu. I'm an ardent farmer and soil advocate in Nairobi, Kenya. I run two companies. One is Green Dreams Tech Limited and the other is Archaea Kenya Limited, both of which optimize smallholder farming practices and systems in Africa through the iCow regenerative agricultural e-extension platform and ecosystem. And this is part of that ecosystem. I've been farming for over 24 years now, but it was only a few years ago that I really began to understand and fall in love with soil. It really started when I stumbled across and took the Kiss the Ground course in soil advocacy. There's a really interesting experiment in this course called the soil integrity test. And I watched it and I tried it. And when I did it, I knew right then that this was the lever that we could and should use to show farmers the actual state of their soils on their farms and at no cost. I knew that this would start the conversations and the demand for fixing degraded soils. So I started a small soil advocacy program using Zoom, teaching interested students across Kenya what I'd learned. The program design required onward teaching by my students to engage families, to engage with families and communities in learning and building soil health. My students, who now number over 250, didn't want our classes to end. So we formed the iCow Soil Advocates Monthly Forum to keep us united, inspired, and connected in our collective passion for soil. And all the while, I continued my own learning through the famous Elaine Ingham Soil Food Web School, finally qualifying last year as a certified soil lab technician. 6 of my students are taking the course too, and 2 are ready to take the lab tech course, which is so cool. If any of you in the audience have ever contemplated doing this course, just do it. You'll love it. If I can do it, anyone can. Most soil scientists would agree that the science of soils and soil life is incredibly complex. To non-scientists, it can be overwhelmingly mind-boggling even. Yet, soil life is incredibly intriguing and it's so darn fascinating. And here's a funny thing. Who would have thought that a lawyer would be the best placed person to distill the science of soils for non-scientists? I mean, a lawyer. Well, Today, we're so incredibly lucky to have this lawyer join us to tell us his soil story. So, ladies and gentlemen, please give Jeff Lowenfels, famous author of the award-winning Teaming series, a huge round of emoji applause. And Jeff, over to you to take us underground.
All right. Thank you for that nice introduction. I don't deserve it. I am just a lawyer. I am a follower of Elaine Ingham. She is the guru. I'm a follower of Dr. James White. He's another guru, and I'm a fraud. But what I am is not very smart. And so, in order to understand this wonderful system which Dr. Elaine introduced me to, I had to really try to dumb things down. And in doing so, I think I stumbled upon a way in which those of us that are doing this can explain what the soil food web is in a simple, easy way. Now, most of you people already know about the soil food web, so this is going to be a little bit of old hash, but I think if you listen carefully, you'll pick up some tips on how to explain what the soil food web is. And the celebration for this particular talk today is the fact that the soil food web, which we were introduced to by Dr. Elaine Ingham back in the early 2000s, has expanded as a result of the ability to see things better. Microscopes have improved. We have new kinds of microscopy, and things which were not available back in 2006 when the first Teaming with Microbes was written, the first book was written, are now completely different as a result of the way we can see things. So what I'm going to talk about today is what I call the new soil food web. And I hope this works. Let's see. Yes. All right. Well, in my other life, I'm known as Lord of the Roots, and that's really because I had these 3 books, and now just in November, the 4th book came out, Teaming with Bacteria. So now I have what's known as a quadrilogy. I live in Anchorage, Alaska. This is a sled dog doing some business up here in Anchorage, Alaska. You know, people think Anchorage is a really cold place, but it isn't, not all the time anyway. And we garden, and we have beautiful gardens. We grow lush gardens, and we have nice lawns. This lawn looks like it doesn't have dandelions in it, but it's full of it. And we grow lots of different things that people don't expect. We grow fruits, but of course we grow them behind fences because we have moose, which is certainly an animal that is not available in Africa. So that's our difficult animal to garden with. You know, I used to be a chemical gardener. I used Miracle Grow for a reason which we can explain later on, but my family had a connection with the founder of Miracle Grow, and he gave me this particular box of Miracle Grow actually when he visited my property. And to me, it didn't matter whether nitrogen, which a plant needs, comes from a brown manure or whether it comes from a green powder. It was nitrogen, and nitrogen was nitrogen. And then one day, a good friend of mine, a fellow garden writer, sent me this particular picture. He added the words, the soil food web. And then he said, oops, well, let's go this way. Well, I got to go backwards. I'm sorry. He sent me this picture. I didn't know what it was. He told me it was the soil food web. I looked it up. I discovered Dr. Elaine Ingham. I read about it. I still had no idea that I was looking at a nematode. Nematodes are blind. They travel through the soil and they smell what they're looking for. And this particular guy was looking for this tomato root. And as it was swimming, it swam through these 2 little lifesavers. This is a single fungal hyphae. And when it hits that second one and this thing gets rubbed, it fills up with water, both of them do, and strangles the nematode and prevents it from getting in at the plant. Wow. I had no idea that was happening in my soil. This was about 1996. And then, of course, you lose. I lost because I used to bet with people that nitrogen was nitrogen. It didn't matter what form it came in. And Tom showed me this. He said, I lost. he put the word soil food web there, and I couldn't figure out why I lost. And so I did a tremendous amount of investigation and stumbled upon this 1988 Dr. Elaine Ingham picture. And I had no idea what I was looking at. I was the longest garden writer in America at the time. Mycorrhizal fungi, I had no idea what I was looking at. Fungal feeding nematode, what is this? And so I had to do a little bit more research, and I came upon this particular picture. This is a slide I could do the entire show on. Basically, what happens is that the sun, photosynthetic energy from the sun, is used by the plants to produce carbon-based substances that drip out of the root system and attract fungi and bacteria who need the carbon because they can't produce their own. And so they move to the rhizosphere, the area right around the roots, and they eat these exudates, and they consume these exudates. And as they do so, they in turn attract the things that eat them. So protozoa and nematodes are the two things that come as a result of fungi and bacteria being around. Protozoa can eat tremendous amounts of fungi and particularly bacteria. Nematodes can eat both, and they eat them also because they need carbon. They don't eat everything that's in the bacteria and the fungi, and so they excrete the excess. And what's excreted turns out to be plant nutrients in plant usable form. Whoa, okay. So the plant puts out the exudate attracts the fungi and the bacteria attract, and fungi attract the nematodes and protozoa. And then the bigger guys that eat the nematodes and the protozoa are also attracted. So you have a soil food web. Everybody knows what a food chain is. The little guy gets eaten by a bigger guy, gets eaten by a bigger guy. That's a chain. And there are thousands, millions of these chains in the soil. And every now and then something on that chain looks up and says, hey, I can eat something off of the chain above me or below me, and does so and connects the chains together, forming a web. It's really just a sort of a way of describing who eats whom in the soil food web. It's very complex, but on the other hand, it can be very simple. So I'm not going to be describing these guys, the bigger guys. I'm going to concentrate on the microbes, not the microarthropods and the arthropods that are in the soil. These are very important. They're covered in teeming with microbes. We can answer questions about them. I've got other presentations about them. But today I'm going to concentrate on the exudate-attracted bacteria and fungi. And you're exudating right now. Sweat is exudate. And it does basically the same thing. It attracts fungi and bacteria to your skin. And if those soaps that they advertise on television actually killed all the fungi and bacteria, you'd probably be dead in 24 or 48 hours. So you're exudating right now as we speak. That's okay. I am too, that's for sure. This is a root tip. And if you can look very carefully, of course you can, this area right here is the area that the exudates are introduced into the soil area, and it attracts the life that comes as a result. So this is how it works on a really simple basis. There are a bunch of trees here, and this is Wisconsin, and it's a hot, sunny summer day. It's a Friday afternoon, and this tree says, I want to have some Japanese food. And the tree next to it says, no, well, let's have Mexican food. And another one goes, no, let's have French food. Well, the Japanese the tree wins out because it's bigger. And so these are the roots of that tree. Let's put it root system. And so what it does is it produces an exudate and drips it out into the rhizosphere. And it's designed specifically to attract Japanese fungi and Japanese bacteria. Simple as that. And if the tree wanted, say American food, why, I don't know, it would simply change the exudate that goes into the soil and attract the kinds of microbes that produce American food. The plant is in control. We like to think we're in control as gardeners and farmers, but if we are smart about it, we'll let the plant do as much as possible without interfering into their system. The plant is in control. Not only is the plant in control, but it takes the organic matter that plants need but can't use because it's in organic form and converts it to inorganic forms and puts a charge on it so that it can get into the plant and then be utilized by the plant. And that's what my second book, Teaming with Nutrients, is about. Again, I'm not really going to go into that. If you want to delve into that, you can pick it up in the book. So what we're talking about here is sort of the soil food web progression from 2006 to today. So what you just saw is what I call micro-mediated solubilization of soil nutrients. What happens is the nutrients are freed up and then they move through the soil through different mechanisms, osmosis, direct flow in water to the root system, where they are then absorbed and utilized. That's the basic original Dr. Elaine Ingham system. And I have to tell you, when I learned about it, I was blown away. I walked around for a month, completely blown away by what Dr. Elaine had discovered and described. Well, not all of the bacteria, it turns out, we now know, are eaten and then their poop or whatever the excess is goes into the system. There are two kinds of microbes, the bacteria and fungi that are attracted, that don't operate the same way. They're not consumed, and yet they still help the plant gain nutrition. And the first one are mycorrhizal fungi. And mycorrhizal fungi basically came into the fore around 2008 or 9. They were becoming commercially available. And so people started to learn about the mycorrhizal fungi symbiosis, which was a new branch to the soil food web. So the mycorrhizal fungi basically associate with the root. And you can see there's quite a difference in size. And so the fungi themselves are able to go into soil pores that the root itself could never get into. This is a symbiotic relationship, and in return for the exudates, which attract the fungi to the plant calls these fungi to them. The fungi go out into the soil and bring back all manner of nutrients, and then deposits those nutrients into a little transfer vesicle that sits in between the cells inside the root. And so you get all of these wonderful nutrients, particularly phosphorus and nitrogen, as well as water being brought to the plant. 90 to 96% of all plants on the planet Earth form a mycorrhizal association, which is known as a mycorrhizae. The ones that don't generally tend to be plants that your kids don't like to eat. Cabbage, kale, Brussels sprouts, broccoli, the cole crops. And then, of course, there's some fruits. Blueberries in particular have their own kind of mycorrhizal fungi, which we can't duplicate. But 90 to 96%, most of what you grows using mycorrhizal fungi. And here's how they operate. So we got two seedlings, they're sitting around in your garden, and one of them says, I really could use a bologna sandwich today. And so what does it do? It goes and it mixes up the right exudate. It puts that exudate out into the soil, and it catches the fungi that's going to go out and get a bologna sandwich and bring it back to the seedling. And sure enough, it does. And once it does, it continues to feed the plant so that the plant grows. Wow. And even more amazing, in some instances, when you have plants next to each other, they will share their mycorrhizal goodies. Wow, that's really an amazing thing. So what you've got so far is the Dr. Elaine original basic system. She mentioned mycorrhizal fungi, and of course, it's part of the soil food web she discusses right now. We had that mediated system where through diffusion and interception, the root grows into the food zone, or you get mass flow. That was the 2006 Teaming with Microbes version. And then we've got the mycorrhizal fungi version where the mycorrhizal associates and goes out and gets food. And now we know that there is a third one called the endophytic bacterial symbiosis. Endophytic bacterial symbiosis. Endophytic, inside the plant, endophytic, and of course, bacterial symbiosis. There's a new part of the soil food web, and it's known as the rhizophagy cycle. Rhizo, root, phagy, to feed on. It was discovered by an Australian. She was at a university in Australia and came across what she thought were literally bacteria being absorbed, eaten, engulfed by roots of a plant. And she called it rhizophagy. Apparently, the group that she was working with lost their funding. And so this was a 2010 discovery that languished for a little while. I remember being told about it and I couldn't find much about it. And then one day, it really started to come into the fore. Now, we're talking about bacteria. And when we talk about bacteria, you are never looking at one. Okay, don't think about one. When someone says bacteria, we tend to just, bacteria, maybe thinks of something like this. You should be thinking this way. There are gazillions, never one, always lots and lots of bacteria. And they multiply every 20 minutes, which is why there are lots and lots of bacteria. I stole this photo. I hope the author's not watching. This is the tip of a very sharp pin. And these are all bacteria, bacterium on the tip of a very sharp pin. Don't think of one, think of many when people say bacteria. This is a single cell in your tongue. And these are bacteria in the slime that coats. They form slime in order to protect themselves. And oh my goodness gracious, look at that. That's one single cell. And this is all the bacteria. So we're talking something that's extremely small and incredibly plentiful and basically ubiquitous. They're everywhere. And they can be really, really beautiful. They're just amazing, amazing organisms. Unfortunately, Sue and I were talking earlier this week. In America, I don't know about Africa, we start our children out learning about dinosaurs, which are extinct, and other than the fact that they provide oil, really are useless. Instead of teaching them about microbes, we should be really concentrating about microbes because they have a purpose and they're so important. This is a mite, which is incredibly microscopic, and they're the bacteria. So they're really small. They're really small. All right, let's see here. So this is what we were left with after 2010, bacteria inside a cell. Well, how'd they get in there? What were they doing there? This 2010 rhizophagy was too curious a phenomena to be left alone. And so there was a group in New Jersey led by a Dr. James White, who picked up the cudgel and really defined and refined what rhizophagy is all about. So again, here's our root, and here are those exudates that are being dripped out. These cells at the tip of the root are extremely new and very, very thin-walled. And here is a bunch of bacteria that's been attracted to the root tip. The exudate zone is here, and these have been attracted by the exudates. And a lot of these, they're eaten, these guys, but a lot of them form a very tight slime colony where they live right up against the root, and they live off of the exudates. Now, all of a sudden, some of them begin to smell what this is the bacteria inside a slime. They're very happy, but they begin to smell a buttered popcorn smell. I don't know about you, but buttered popcorn is one of my favorite foods, and apparently some of these bacteria love it as well. And so they smell this buttered popcorn, and it actually causes them to leave their slime colony and to move towards the butyric acid smell that's being emitted by the plant. And so it causes them, they really want to get at it, to break through one of those thin root tip meristem cell walls. And it breaks through the cell wall, and it ends up in this little area known as the periplasmic space. So this is the cell wall. And if you see this little zone in here, that's the periplasmic space. It's a liquid. And so they break through and they find themselves in this periplasmic space. I think the easiest way to demonstrate that periplasmic space, I don't know about in Africa, but in the United States, we have these tofu packages. I think you probably have them as well. And so this is the cell wall right here. And this is the periplasmic space. And then this is the cytoplasm with all the organelles and everything else. And so the bacteria, they break through the cell wall and they end up in this little periplasmic space that surrounds the basic innards of the cell. And when they do so, the plant, there they are. See, they're just, this is the periplasmic space. You can see all these bacteria. They've been stained in order to demonstrate that they are in fact bacteria. Here's a picture of a different kind of bacteria, and you can see that they're all in this little area on the outside. So what happens is that they move in, and once they're in that periplasmic space, the plant sprays them with a strong substance known as a reactive oxygen series. And it does so to strip off the bacteria's cell wall. So it sprays the reactive oxygen series. This is a really pretty strong oxygenator. When you get sunburned, you're experiencing ROS when you get sunburned. This is even in the United States, people will appreciate, this is ROS getting sunburned. But in any case, that's what causes sunburn, this ROS, and it strips off the cell wall of the bacteria, which is then absorbed by the plant as nutrients. Now, at the same time that it's spraying the bacteria, the plant is spraying itself. And so it has to be able to withstand the spray. And this causes the plant to develop a resistance to stress. So it's not only stripping off the bacteria using this spray, but it's improving itself as a result of exposing itself to the spray, which sounds counterintuitive. Now, the bacteria doesn't take this lightly. Even though it has its cell wall stripped off, it's still alive. It's called an L form. It's still multiplying every 20 minutes, maybe even faster, because it doesn't have to worry about the cell wall. And so in order to protect itself, it does two things. The first is it generates ethylene into the periplasmic space. Now, ethylene is a plant hormone, and one of the things it does is it causes the plant cell to stretch. And when it does so in this particular instance, the ethylene mixes with the ROS, the plant cell is stressing, but you still got this going on, and you get carbonic acid, and then it weakens the ROS so that the plant wall is safe, and the bacteria that's left over without a cell wall is also safe. So there's a weakening of the ROS by this ethylene, but it also causes the plant cell to stretch and to provide a little teeny bit of carbon to it so that the bacteria stay alive using this carbon. So it's causing the plant cell to stretch, but it's also causing the plant to give it a little bit of carbon. And it also carries a nitrite generator. And it does the same thing. It sprays the nitrite is in the form of nitric oxide, which is converted to nitrate, which further weakens that ROS. And, oh my goodness gracious, it's nitrogen and the plant absorbs it. The bacteria is literally fixing nitrogen inside that periplasmic space. It's not like rhizobia, which requires a nodule. This is happening inside the plant cell. Well, it's a trap because if the ethylene isn't provided, then the bacteria wall-less doesn't get the carbon. So it has to continually provide that ethylene in order to get the carbon to stay alive. And if it doesn't provide the nitrogen, the ROS begins to take it over. And so you get these two cycles that are going on, and the bacteria is trapped inside the periplasmic space. Meanwhile, the nitrogen, including the nitrogen as well as the other nutrients that are in the bacteria cell wall, are absorbed. Happy plant. Up to 40% of the nitrogen that a plant utilizes can come from rhizophagy. 40%. Wow. That is an unbelievable number for something we didn't even know about until 2010 and didn't even really understand until 2018. All right, so you've got these bacterium and they're wall-less and they're circulating around the periplasmic space because you get cyclosis inside the cytoplasm, and so you get some of that imparting here, and they're circulating around producing ethylene. Whoops. And then, so they're circulating around, they multiply. These are quads of wall-less L-form bacteria. These happen to be in the periplasmic space. You can't really see it because of the angle there. Here's more as they continue to grow and multiply inside the periplasmic space. And then eventually what happens is you get crowding. You get so much crowding that they back up against the wall of the periplasmic space. And this is the plant wall. They back up against that plant wall. They're still producing ethylene, but instead of getting circulated, it's being produced in a concentrated area, as is happening. And the ethylene forms a tube out of the cell wall. So you've got the cell, and then a tube forms as a result of these bacteria getting trapped right there, producing ethylene. And we know these tubes as plant hairs. Now, this is where I always have to sit down and pinch myself. Plant hairs are not formed in order to bring nutrients into a plant. They're formed in order to bring these wall-less bacteria back out into the soil. They happen to be extremely thin-walled. Remember, the meristem itself is very thin-walled. These are even thinner. And so they've got the capability of being able to let nutrients in. Again, read Teeming with Nutrients, which I probably have to revise now because of this particular issue. But it's an unbelievable thing that these are not produced to take in nutrients. They're produced to eject the bacteria, because what happens is the bacteria move into those tubes, and here they are in the tubes. And there's some you can see here, this is the cell. This is sort of where the tube forms. It's all part of that one original cell. It's not two cells, it's the same cell. And the bacteria begin to move into it. And as they move into it, again, they're producing ethylene. They move into these hairs. The hairs begin to grow. They're stretching ethylene. They're stained, again, just to confirm that they are, in fact, producing nitrogen. And then they get to the tip. And when they get to the tip of the growing hair, they're blown out into the soil where they regrow their cell wall. And here they are. The staining shows you the bacteria. They're being blown out back into the soil. Here's another picture. It doesn't always happen just once. As the hair grows, you can have 1, 2, 3, 4, 5, 6 explosions. So here's one that's exploded many times, putting these bacteria back out into the soil where they regrow their cell wall and obviously replenish other nutrients. And then guess what? They go back into a new meristem cell and repeat the trip again after about 2 days. It's incredible. It's a cycle we call the rhizophagy cycle. Now, you may hear it pronounced differently. And again, I was speaking with Sue. The reason why you hear it pronounced differently, I think, is because it was originally pronounced by Australians who don't speak like New York people. And so I say rhizophagy. They may say rhizophagy or something of that sort, but I think rhizophagy is the way to pronounce it. And it's just a beautiful cycle that's been going on for eons and eons. When you think about it, the plant has had to adapt to letting these bacteria in. Now, they may fight with them with this little spraying of rasa or whatnot, but they let these bacteria in and they let them live. They let them go out and they let them back in again. This has evolved over eons and eons. And it's unbelievable because these plants all grow using this system. And the big companies have now discovered that this system exists. They've read Dr. White's paper, and all of you should read Dr. Elaine's, anything she writes, and anything Dr. James White writes, you should read. They've discovered that, hey, maybe we can put this more nitrogen directly into a corn plant, not just in the roots, but elsewhere in the plant. Have other endophytic bacteria that can feed the plant as well. And so that's the holy grail now. Instead of using chemicals, people are looking for a way to be able to use these kinds of things. Oops. So in the past, we looked at the soil food web and the plant as a farmer. The plant was putting out the exudates and then harvesting the corn. That's farming. And now we've got a knowledge that the plant, in addition to farming, is also ranching. It's putting out, it's taking the bacteria, shearing off their wool, eating a couple of lamb chops, and then putting them back out into the paddock again to regrow the wool and bring them back in. So the plant is a farmer and it's a rancher, which is pretty amazing. Now, there are other kinds of endophytic bacteria, and I just mentioned that they are becoming the holy grail of the chemical industry, who want to convert to bio as opposed to chemical. And those are called endophytic bacteria as well. And some of them have also been able to pair up with individual kinds of plants in order to live and thrive inside a plant. Now, why would a bacteria want to move into a plant? It's pretty simple. It's safe inside the plant. There's no competition inside the plant. The prey, the nematodes, not inside the plant. And so they can go in the plant and repeat what they need to be doing, which is multiplying every 20 minutes. And it turns out we've got the rhizophagy endophytic bacteria, but as those root hairs grow, little cracks appear. And other kinds of, endophytic bacteria move into the root system through these little cracks. They might move in through a tear or some damage that might have occurred as the root was growing. They might move in through the stomata above the plant, but they definitely move in around the root hairs. They get into the plant and they move up through the system into the plant where they do various things. They produce 5 or 6 phytohormones, which I think I have a slide of, and we'll talk about them later on. But eventually what happens to these bacteria is they end up in the flower. And as they're in the flower and the flower is producing seeds, they get trapped inside the seed. And there they are inside the seed, so that when the seed is planted, they can not only help the seed germinate, but they can jump off the seed into the soil where they provide the right kind of bacteria to either be endophytic in the above ground or even rhizophagy below ground. The seed can bring with it the kinds of bacteria that it needs. Now, to show you how strong this is, there are studies that take a 400-year-old strain of corn. It has the same bacteria today that it had 400 years ago. And they're not the same mix of bacteria as the 225-year-old strain of corn that we're growing today. This is how you get heirlooms. You grow and you grow, and you get this relationship between the bacteria in your area. They get into your plant, that your plant lets in there, and it becomes part of your plant's system. Whew. Pretty mind-blowing. So you get the bacteria in the seed coat, and I'm trying to remember what the numbers are. There could be 9,000 different kinds of bacteria in a teeny little seed. Wow. There's also in there an entire embryo of a plant. It's just amazing. So these are the phytohormones that some of these bacteria that are endophytic can produce. Gibberellic acid. It was discovered, back in the 1950s. I did my very first science fair project on gibberellic acid. It made coleus plants grow quickly, extend, and get really tall. And today, gibberellic acid is being used for all of these things, fruit development in particular, strawberries, et cetera, et cetera. Auxin, of course, everybody knows what auxin is. It's a growth hormone, and it's very important for fruit development and for flowering. Cytokinins, very important, particularly at the start of a plant's growth, stimulates the use of nutrients. Ethylene, we've already talked about. Ethylene, by the way, is also important for flowering and fruit development. These are all very important hormones produced by bacteria. So it's another reason why a plant might allow a bacteria into a system without getting infected, without trying to repel it. They're helpful. So you get this stress situation again in the plant. In order to be able to handle the bacteria internally, it has to develop stress, its own stress. And so all of these things are developed and induced systemic resistance. These are the different things. And again, stress tolerance for drought, blah, blah, blah. It's all as a result of these endophytic bacteria. So you have abiotic stresses, which they can handle. There are certain places where you can be on one side of the street and the lawn will be covered with snow. The other side of the street, the lawn's still green, the snow doesn't stick. Why? Because there's a bacteria that is changing the freezing point of the water.
Wow.
Heat, drought, metals. There are bacteria that produce cytophores, I think that's how you pronounce it, that jump off the plant, go into the soil, cleate iron, for example, tie it all up so that it doesn't poison the plant, or cleate arsenic so it doesn't poison the plant, or brings it back into the plant so that the plant gets what it needs. And then, of course, you get the biotic stresses. It's able to produce the kinds of things to fight off attacks from biology. This is the cytophore situation, cleating up the iron. Pretty amazing. Now, you can buy today, particularly farmers, not a lot, you can buy 3 basic bacterium, which are very, very useful and which end up endophytically. This one's a little bit more difficult because it's storage is always the difficult part. That's what the big companies, I am sure, are working on. How do you store this stuff so you can use it? But these are available, and you can buy these. And in fact, you can buy them in a lot of nurseries in the United States. So you can definitely get them at commercial agricultural situations. And if you can't, ask for them because they're important. They work. Farmers all around the world are using these, and there are different aspergillium, for example, or they're different species based upon, not species, varieties based upon where you're located. So you may even have some specialized ones that have been developed for your particular area. Now, in addition to rhizophagy and endophytic benefits, it's important to recognize that these bacteria, along with the fungi, tie up soil particles. They're the beginning of the creation of soil structure, which is then amplified by the bigger critters that are making tunnels and larva spaces and burrows and bringing organic matter down like worms do, et cetera, et cetera. The soil structure comes from the bacteria and the fungi in the soil. And they're very, very, very important. And we're not treating them properly, and we need to. So a takeaway that's pretty obvious is that plants are pretty much in control. They do the rhizophagy, they do the endophytic bacteria entrance and creation of the seeds and everything else all by themselves. They don't need us to help them at all. What we do is we mess up the system by thinking we're in control. You need to start thinking about the plant as in control. And they're very, very amazing. They can do incredible things just because they don't run around, and just because they can't speak English or French or Swahili or whatever, doesn't mean that they're stupid. They're very beautiful, and they're very, very important and effective. Chemicals obviously have a bad negative impact on rhizophagy bacteria. It kills it. Or it kills the food that maybe some of the rhizophagy bacteria need before they get into the plant. Pesticides are designed to kill pests. Well, they're not specific. They kill lots of stuff. So chemicals have very, very negative impacts. Organic materials obviously do not. And the big impact also is to these guys as well. And so when you have the use of chemicals, you end up with less rhizophagy, nitrogen fixation. You get much less mycorrhizae, which is less nitrogen, less phosphorus, less water. Unbelievable that we continue to use these things. And when you don't have these things around, not only are you getting less, but you're getting upset because you want your plants to be healthy. You want to make money off of your crop. Guess what? You have to become the fungi and the bacteria. You need to become the bottom of the soil food web, because without them, you're going to end up having poorer plants, all these problems, dependency, disease, lack of nutrition. It's going to be, and your plants won't multiply. They won't get to a breeding stage, which is also not very good. With the loss of that soil structure, we are really in deep trouble. And the way to return that soil structure is to create conditions that treat the bacteria and the fungi properly. I don't know whether it's true we only have 60 years left, but we are losing soil inches a year here in the United States. We're finding that some of the soil in the United States comes from Africa. So we're losing soil because we're destroying the soil food web, particularly the bottom parts of the soil food web, the bacteria and the fungi. Best practices, well, mulches. The first best practice is to obey the law of return. What falls down from a plant is in nature is supposed to lay there, decay there. It feeds the plant. You get this great cycle. We're farmers. We take things away from the soil. We take the corn cob, we take the apple, we take whatever the fruit is, the tomato, and we consume it or we sell it. And that means we're violating the law of return. And what we need to do is ameliorate or pay for or fine for violating that law of return. And you do so by using living mulches, dead mulches, wood mulches, green mulches, compost, soybean meal, bacterial meal, organic inputs. Oops. Monitor and know what's going on. You need to really know what your NPK is. You don't have to monitor that every single crop, but it's nice to know what your NPK is and whether it's changing over a 4 or 5 year period. It's better to know what your biomass is doing, what your microbiomass, that biomass of microbes is doing. And there's now a way to measure that using the microbiometer. So if you go to www.microbiometer.com, you can buy a kit and then you can test in your field for $5 or $10 American dollars a day, exactly, not a day, a test, exactly what's happening to your biomass. Is it increasing as a result of what you're doing, or is it decreasing as a result of what you're doing? And Sue and I have talked. I put Sue in touch with the people who make the microbiometer, and I'm hopeful that she's going to help get that available around the country, around the countries, so that those that can't afford it can take advantage of this test. It's really a great way of knowing what you're doing. Of course, looking through a microscope, if you can do that using the soil food web system, is also a great way of knowing what's happening in your soil. I like the biometer test because you can really tell, and it's very easy to run. Now, other obvious takeaways: don't sterilize your seeds or your soil. Use mulches whenever you possibly can, whether they're live mulches or whether they're dead mulches. Don't throw away used soil, particularly if you're growing in a greenhouse. It's got all manner of soil food web life in it. If you've been treating it properly, you can recharge it if you need to with a little bit of compost, reuse it. And compost. There are any number of ways of composting. There's a specific composting that's been developed. I think it's called the Sue Johnson system, or the Johnson-Sue system, that's been developed for Africa. But just conventional composting works quite well. And then you can end up with compost extracts, compost teas. It is highly, in fact, the number one thing that you can be doing as a farmer, if you're not doing it already, is compost. Make compost. Compost has all of the nematodes and all of the protozoa, which I call the fertilizer spreaders, and all of the little guys, the fertilizer bags, which are the protozoa and the bacteria and the fungi. It's easy to compost. I know that it's not in the African culture. It had to be rammed down the US culture. And more people here in the United States are composting, and everybody should be doing it. It's just sustainable. And when you hear the word regenerative, which I don't happen to like because it's being co-opted, what they're really talking about is putting everything on your property back into the soil that you possibly can, and that's composting. And you can make composting using the same plants that are on your property, which is, I think, a great way to go. And you can use worms. I hope you can use worms. They make a phenomenal compost that has a higher concentration of nutrients than the components that go into making the worm. It's a fascinating thing, and they're really, really wonderful. And you should experiment using different composts on your crops. Vermicompost has a different mix of bacteria than thermal compost. And some plants like the thermal compost better than the vermicompost. Experiment. Find out which ones your plants like the better. So some not so obvious takeaways: you need to read these books. not because I wrote them, but because they're simplified and they contain the information that you're going to need in order to do what Dr. Elaine, has said to do what Dr. White has said to do, and that is farm using the soil food web, not chemicals. So, not convinced. I ask people always in the United States to think about this: the redwoods, and of course, you've got comparable trees all over Africa as well. How did they get so big? How did they get so old without anybody ever applying a commercial fertilizer or spraying them with an herbicide? They teamed up with these microbes exactly like you should, and you'll have plants that are equally as impressive as those. All right, that's it. If you have any questions you want to ask, we'll of course try to get them now. You can write me at jeff@gardner.com. I don't always answer right away. Again, I want to also point out, I did not invent this stuff. This is Dr. Elaine Ingham, Ingham. You should be reading anything that she publishes. And this is Dr. James White and his students. He's at Rutgers University in New Jersey, the United States, and he is constantly upgrading the knowledge we have about rhizophagy and endophytic bacteria. So there we go. And let's see, I can maybe get rid of this.
Wow, Jeff, you've, no questions have even come in because everybody has just been like glued to your presentation. I mean,
well, I thank you for giving me the opportunity to be able to put out there what I think Dr. Elaine and Dr. James White are saying.
You did a fantastic job. I mean, you're such a great communicator. You've communicated it in ways that we can relate to. And I love your analogies and the humor that you bring into it as well, because it's serious stuff, but you put an edge on it that makes it, we remember it more. I have two questions for you.
Sure.
But before I go there, I'll leave my questions until the end. James, I would like you to unmute Paul Fungu. And Paul, I would love him to have a conversation with you, Jeff, about what he is doing and what he did. So Paul is one of my students who is really taking the farming with biology to another level. And recently he had a bumper crop in his maize fields. And it was actually really amazing. So I wanted to talk to you about what he did. I want you guys to just have a little bit of a conversation about what he did. And maybe you can explain to us in detail what was actually going on at a microbial level. Because a lot of us just look at it and all the farmers around him are thinking, it's some kind of magic, what was going on? So Paul, over to you both.
Okay, thank you, Sue, and everyone. That was really
Can
lovely.
we get him on camera?
Okay, you like my camera?
Yeah, if you can come on camera so that we can see you.
I think I need it enabled by the host.
Okay, let me just find your. Who's? Can you do that? Can any of the? Your name must be up at the top now because you're speaking. There we go. Okay, let's see. Okay, I'm just going to make you a co-host so that you can then unmute. You can show your camera. Okay.
Okay.
There you go.
All right. Thank you. Sorry, had a very long day and long night. I've been very busy. That's why I'm looking a bit sleepy. Yes. So what we've been doing with the biology, basically, is as you know, doing a lot of extracts and composts, and that is what we apply out there. And the approach, normally we use the IMOs as suggested on the charts, and vermiculture, and a lot of
you said biochar?
IMOs and vermiculture.
Oh, vermiculture. Okay.
Yes, and a lot of these other inputs that are KNF technique, that is Korean natural farming, ferments. And
right.
The response with the crops has been really, really amazing. Putting them out on maize fields, we were able to see a lot of vigor in growth, very good yields, a lot of pest resistance, virtually zero disease, and well, it's like magic. Right now, there is a field that we are working on a side-to-side comparison for a client, and he cannot believe that we are actually at early stages of a crop, and the biology side is looking already much better than what you would have expected with all the money that is put in with the synthetic inputs, and it's really, really amazing.
Yeah, I think what you have is a perfect example of what happens when you convert to the soil food web system. We really we really don't appreciate that the plant works better when it's working naturally, as opposed to being force-fed the nitrogen that you think it should be taking up. It takes up what it needs, and it puts it together in the way it needs to put it together when it has the natural inputs. And that whole system gets destroyed, obviously, by the chemical inputs. What you've got there, you've got the KNF, and you've got, did you say you had biochar as well? I was putting in just yeah, well, I was putting on my earphones, so I missed the full description. So it's KNF inputs and vermiculture. Okay, yeah. All right. Well, of course the vermiculture, God, it's such an unbelievable thing. So yeah, when you put the vermiculture on, I don't have the slide, but you can Google and find the number. The concentration, again, of things that come out the end of the worm, it's got a much higher concentration, like 7 times more phosphorus and 6 times more potassium, et cetera, as a result of the concentration. So what's happening inside the worm, I don't know if you're familiar with this, but the worm takes in that organic leaf, let's say, and it takes that leaf in and it gets into the worm system. The only thing the worm wants are the microbes that's on that leaf, an occasional bacterium, an occasional fungi, the microbes. It doesn't eat the other stuff. And the way it gets those microbes is it crushes up the stuff as it goes into the worm, and it gets crushed up. You can actually see the worm when it eats, crushing it up, and it creates a liquid which the worm gets its stuff out of, but the liquid, sticks in that stuck particle, and it gets crushed up again and again and again as it moves towards the end of the worm, and that liquid becomes richer and richer and richer, and it's in this little pellet that's been created, and so when it comes out, it's got this great nutrient stuff in it. And I suspect what's happening is that increased, first of all, the natural system, but second of all, the fact that the vermicompost has such great nutrients in it that you've really, really increased the nutrients availability for your plants and given it the nitrogen and everything that it really needs. Really exciting. That's a great example.
Yeah, and I think that Paul also mentioned to us at a time there was an armyworm invasion, and it affected all of the farms around. And his family were like, "You need to get ready. You need to spray. You need to." And he was like, "No. Let's just watch." And he wasn't affected. His plants withstood the armyworm infestation. And just last week, we heard of another farmer up in Makueni who did exactly the same thing, who went into non-till, growing maize first in a seed bed, taking it out. I mentioned that earlier before we started. So as opposed to just growing seeds out in big open and cleared fields, they left their fields undisturbed while they were grazed right down to nothing, and then planted maize in little seed beds, and then took the maize out at just 3 weeks before the rains, watered them 3 times a week up until the rains came, and they only had a month of rain, and they've got a bigger yield than they've ever got before. Same thing, using biology, using compost when they planted it out and not disrupting the soil.
Right, and they might have even gotten even better results had they put mycorrhizal fungi on the corn before they transplanted it into the soil.
Is that me or is that Jeff?
When they took it out of the seed bed and then they put it into the field. And so at that point, even though there are mycorrhizal fungi in the field, no reason not to put it in. And actually what they could do is collect soil from their best plants this year, and maybe try to use that when they plant the seed beds next year. And in fact, when they plant the seed beds, they may want to put mycorrhizal fungi on the seeds themselves, which of course is the earliest time you can do it. Yeah, there you are. You're there. I can't see you there, so I don't know whether I'm there or not. But someone asked another question. I do these, but yeah, this is the way to go. You know, we've been tricked into using these chemicals, and we become reliant upon them. It's a terrible, terrible thing.
And not only that, we're using chemicals, and we're using them on seeds that have been grown badly. So we're not getting that seed biome, the bacterial benefits that come in with the seed. So we're just so reliant on this whole chemical input kind of system, and we really do need to get smarter.
Right. Yeah, it's terrible. I mean,
there is a question in the group here, and this is from Shane Plath. He says, sorry, are different crops very sensitive to different compost recipes? Are there solid sound recipes that generally match most crops?
Yeah, you know, I think in my experience has been that if it's good compost, it'll work on any plant. But Dr. Elaine has developed a system, and it makes sense that some plants like a more fungally dominated compost, and some plants like a more bacterially dominated compost. And so you can adjust how you can make designer composts. You change the amount of brown inputs versus green inputs, and you get a more fungal compost. You can also, and it's very important that you have real compost. I think Dr. Lane likes to use the term, it's not compost if it stinks and it's comes off a pile, even though you think it's compost. If it hasn't gone through the system, every part of it, then it's not compost. And so you want to make sure that you've got good compost. You can kill plants by using bad compost that contains anaerobic alcohols and anaerobic things and alcohols. It's not good. So you want to have good smelling compost, good compost, and the kind of compost that meets the criteria of your particular plant. If it's an annual, more green, and if it's a perennial, more brown.
Great. And on that note, we've had a couple of questions here about mycorrhizal fungi. Now, and again, we had an earlier discussion about this, about whether it is in your compost or not. So the questions here are, can you find it in your compost? How do you make mycorrhizal fungi? If you can't buy it, what's the best way of being able to produce it?
Right. You generally don't, it's not in compost because it requires a root, to send out the exudate to cause it to come to life. And so they're not in the compost pile. You add mycorrhizal fungi at the end of the composting process, right before you're going to use the compost, so that the root grows and it gets the signal, and the mycorrhizal fungi also grows. You can grow your own, you can make your own mycorrhizal fungi, and there is a process, a system. It's not difficult. You can find it on the internet. It's Rodale Press and the United States Department of Agriculture. I don't know if it's called On-Farm Mycorrhizal. It's just how to make mycorrhizal fungi, Rodale Press, USDA. And they've got a wonderful system. You use sorghum in those, in a big container, and you can grow your own mycorrhizal fungi. And that's how the professionals do it themselves. So there's no reason why you can't be growing it. It's not difficult. It takes about, I think about 6 months for it to work, or maybe a season. And then once you have them, you have them. Now you've got mycorrhizal fungi in your soils if you haven't ruined them by putting on all these chemicals. And so once you make the application of mycorrhizal fungi in your fields, you probably don't need to add it again. It's there. Doesn't hurt to add it again, and it certainly is helpful to add it early if you're growing plants outside of the beds where they're ultimately going to grow.
Yeah. A couple of more questions. One of them is it okay to slightly rototill just to break up plant residues?
Yeah, that's a good question. People always want to rototill because it's fun. But I've given my rototillers away. The least amount of soil disturbance is recommended. Let's put it that way. So the least amount you can possibly do. By no means should you be rototilling the entire field. You just got one little row. Get a little teeny thin rototiller. You don't have to destroy the whole mycorrhizal setup. And if you can rototill early, before you plant, give the soil 3 or 4 weeks to get some of that mycorrhizal network going again. Don't if you don't have to plant right away, don't.
Yeah. Composting materials and availability of composting materials in areas where it's not so available. So somebody asked, what's your take on this across the globe in USA? I just want to talk about, there are some areas, in fact, this area where they had done this, growing this maize in seedbeds, it's so dry. And literally, as you go through that period of going from one drought to maybe even another rain, just about all of the organic available material is eaten up by livestock, whether it's originally cows and then goats and then chickens, or whatever it is, will eat that stuff up. And then, that's more or less, a situation where we're recommending that perhaps continuing to at least sustain some biology by doing vermiculture in the homestead, so that when the rains do come, you've got some biology to get out there to quickly kickstart the system, even if you don't have the material. We've had people where their compost have been eaten by elephants. We've had places where the compost material has been put aside and then fed to cows. It's the priorities of whatever might be in the area, right?
Right. Yeah, it's difficult. And of course, from my perspective, a compost pile with snakes in it, I'm not touching that.
We had that too. Eric,
yeah,
and
Right. I knew you did. They scare me like crazy. It's an unfortunate thing, and you just need to be looking, if you can find things that can be composted and a source of liquid that can be used. Whether it's gray water and newspapers and the manure, but there are places where you just can't make compost. It's just I don't know what you do. You do everything you possibly can to add organic materials into the soil so that at least during the wet period, you get some decay and some microbial use in the soil. Eventually, what happens if you get enough of it, the moisture stays longer, so you get a dry period, and where most of the area will be dry, the area where the compost pile is and where the compost itself is got more moisture than not. Now, we need to remember that most soil has a a film of moisture around the particles if you've got any kind of structure at all. So you've got some moisture in there, but geez, you know, there are times you just can't compost it. It requires material, and if you don't have it, you're not going to be able to compost. We look for things like seaweeds, kelps, those kinds of things if they're available. If you got a coastline area, algae are very good. And that algae products, I should tell you, Dr. White just told me that the rhizophagy cycle sometimes takes in algae pieces and strips off the bacteria from the algae. Wow. And so rather than compost, maybe you could get a source of algae that you could be adding, that kind of stuff. So it's not a fair world. I guess that's the only way.
One of the biggest, one of the big things for me is, and when I explain this to people who might get composting right, but it isn't composting by itself, because if you put it out there onto land that has got no living roots, it's like putting children out into the wild. You know, they're not going to be able to fend for themselves if they're not being fed. If you're not getting this cycle of carbon coming through the plants and the material on the ground, then you might also just be wasting your compost out there. The question to you is, where you have land like that has no living plants, and you're starting a crop, and you're taking out something like a vermiculture, an extract or a tea or something, and you're putting in your seedlings and you're planting, would you say that the phyto hormones maybe in what's coming out of the vermiculture might start to instigate the microbial community in the soil, in the rhizosphere around those plants? Would that help in that aspect as well?
Oh, no question about it. You know, no question about it. It would help. The bare soil, you know, the naked soil, this is where mycorrhizal fungi can really help. So there's two basic kinds of mycorrhizal fungi. Farmers mostly use an endomycorrhizal fungi as opposed to an ecto. Ectomycorrhizal fungi forms a net around the root, doesn't really go into the root, doesn't go in between the cells, it forms a net. But the endomycorrhizal fungi actually is a multi-carbon compound, and it sort of pulls carbon from the air into the soil. And so that's one area, those virgin brand new where there's nothing there, mycorrhizal fungi would be very effective. But you've got to have the living plant in order for the mycorrhizal fungi to do their thing.
Yeah. And that is one of the big things that actually destroys our land, is because we all think that, okay, I need to open the land and clear it and make it lovely and sterile and then plant. And that's when you actually take 2 steps backwards before you even plan on going forward, right?
That's right. That's right. Yeah, I like to tell people there's no bare soils in nature. I mean, there probably are, but really, nature doesn't like bare soils. This is the decay in the whole system. This keeps the soil food web alive, and that's what you want to be doing. And it's desert areas are difficult, but even in desert areas, you've got which is what I'm calling your description there. You know, you've got algal crusts, and there are microbes there, and there are ways to enhance that, whatever is there. You know, the vermicompost would definitely help it. KNF would probably help it as well. I don't happen to do KNF because it's anaerobic, and I like aerobic. So I'm an aerobic guy. Not that KNF doesn't work; it does, definitely does.
And I guess there's also the just thinking about, the mindset of leaving things like weeds. There's just been an article in the Guardian magazine that's talking about weeds as being super plants now. The weeds that are coming up are they're the pioneers, they're the ones that are keeping systems going, yet everybody's like, oh my God, the weeds, let's get rid of all these weeds, we don't want these weeds, and then start planting. So it's interesting to see that they're being put back out into discussion for their value.
Yeah, like clover, for example, as a cover crop. I mean, if you put in the United States, clover is a pest, it's a weed, but it's a cover crop. It's beautiful. It's terrific. Of course, we use an annual clover, but nonetheless, I mean, we do need to reset our thinking. It's this soil food web system works. You've got people all around the world that are using it. It's how we originally gardened. The only difference is we didn't understand it. Now we understand it. We know how we can live with it. So we don't have to just garden or farm. And when things aren't nutrient anymore, we move. That's what we did in the United States, westward. Now we know we can add things. We know organic material will return. We know that there are ways to add microbes to the soil, and we know there are certain foods that grow the kinds of microbes that we need for our particular kinds of crops. And these are things that exist. We know they exist. There are people all around the world living this way, and yet people still continue to waste their money on the chemicals and destroy the system, et cetera, et cetera.
Thank you. So 2 questions before you go. I'll end with the one on your books, but the big question, the question of the horrible stuff called glyphosate. You mentioned there was some new science on glyphosate and the rhizophagy and bacteria. What is it? What's happening?
Yeah. So glyphosate, which is used universally as a weed killer, and is also sprayed on crops to dry them out, even though it's not on their label. It's not on the label to do that. It's everywhere, and the reason why it's bad for the soil food web is because the glyphosate is designed, or not designed, but the way it works is it destroys a system, a cycle that's inside plants. And we don't have the same cycle, so it doesn't kill us directly. It doesn't kill us because we don't have that system, and in theory, it shouldn't impact us at all. But it turns out bacteria have that system, and the bacteria are killed. And so we've got bacteria in our systems here, inside us, and they're being impacted by that glyphosate. In addition, the glyphosate kills bacteria. That means it's killing the rhizophagy bacteria. So they don't exist. And if the rhizophagy bacteria are killed, then a plant doesn't get nitrogen. And so if it just sprays into your area and it happens to hit your soil, you're losing some of your bacteria. But it's the fact that it impacts the same biological cycle that bacteria have that should be of concern to everybody. Nobody should be using glyphosate. Everybody has it in their bloodstream already. You didn't ask for it, and I don't think you need any more of it.
Wow. So when people have glyphosate-ready plants, what is it that has been adapted in those plants for those things not to happen?
Yeah, I guess those plants don't have that cycle. I guess I don't. It's one of those things. Not my area of expertise, I should say, but they're able to handle the glyphosate. That must mean that the sequium cycle, or whatever it's called, is interrupted or something, or protected. I don't quite
crazy
know.
Stuff.
But anyway, you shouldn't be buying it, folks. It's bad stuff.
Exactly. Bad.
Yeah, and in fact, if you can live without chemicals, you're going to have a much better soil food web, obviously. And people who are listening here, you know that already. I should add one last thing before you ask me the last question, and that is I left out the slide. Your best tool, in addition to Dr. Elaine Ingham's writings and Dr. James White's writings, your best tool is Google. And if you have a question, you go to Google and look it up. And just for fun, you might want to put in Dr. Elaine Ingham in a Google search that'll continually search for it every day. I have rhizophagy, I have microbes, soil food web, and every day, anytime there's any news, any new study, boom, Google will tell you. So you don't even need anybody else. All you need to do is know how to use the Google and you can get all the soil food web information that's being developed as it comes out.
Yeah, you'll be at the forefront. Wonderful. To the last question of the day, you've given us so much of your time and we so appreciate it. You
pleasure.
started off with the first book, Teaming with Microbes.
Right.
Okay.
Right.
And you then went on to Teaming with Nutrients.
Right.
And then
Yeah,
you went
so
on
teaming
with fungi.
Yeah.
And then you did Teaming with Bacteria. So you've
Right.
been writing these books since what? Now it's more than a decade. About a decade.
Yeah, 2006.
Oh yeah, it's more 2006 to 60. It's a long time. So
Yeah.
tell us about why this order, and
Right.
and tell us a bit about
the order is not the order I would read them in, by the way. I would start out with Teaming with Microbes, which I wrote after being exposed to Dr. Elaine Ingham. She is the guru, and so I wrote it for her. And it is, to me, the basic. Some of the stuff in it probably is a little old and maybe something needs to be changed, but not much of it. And I think people should start with that particular book. By the way, it's in many languages. It's in French. There's 2 versions in French, Turkish, you name it. It's got it. So look for it first in your own language. It's on tape, and it's in CD and all that kind of stuff. The second book I wrote was Teaming with Nutrients, and I wrote that because I had no idea how the nutrients which were made available by the Teaming with Microbes soil food web system got into the plant, and once they got into the plant, what did they do inside the plant? How were they used? I would read that last, because the other books are designed to demonstrate how nutrients get to the plant. So the first one is Teaming with Microbes. The second one I would read is the last one I wrote, Teaming with Bacteria, because it adds the rhizophagy cycle. And the third one I would read is Teaming with Fungi, because it's got the mycorrhizal fungi portion in it. And so I think you'll like those in that particular order. And then Teaming with Nutrients will tell you how all these nutrients that get freed up get into the plant. So that's sort of how I would.
Fabulous.
Fun.
Well, guys, the books are all out there. You can get them on Amazon if you can't get them in country. I ordered mine on Amazon, and I got them literally from the time I ordered them. I got them a week later, delivered into Nairobi, and I got them here. And I've read, and I've got them on audiobook as well. I've read 2 of them, and I'm working through. I haven't done Teaming with Nutrients yet, but I jumped into the fungi and the Teaming of Bacteria, as those were cutting edge in my mind and in my studying and in the work that I was doing with the Elaine Ingham course. I love what you're saying about Elaine Ingham and the Soil Food Web course. I am a absolute, call me anything. I'm totally. When I started, I thought, wow, this is a little bit tough, and then it was just like, oh my goodness. And I've got students who are going through it, and I'm trying to get scholarships for students to go through the course as well. We're really working hard on that. We just need the African continent so far has a handful of soil food web trained advocates and soil food web trained students and lab technicians, and we need more. We really, really, really do need more. And I feel that for every lab technician, you're a resource to the continent. So keep going in that direction, because you can move people and microscopes and testing kits with knowledge across borders. We're not allowed to move soils, and we're not allowed to move samples, but we can move. So that's what we need to be thinking about when we're taking these learnings. It's for the continent, it's for our communities. And back to you, Jeff. Thank you so much for joining us, for sharing with us.
I hope you'll join me every week. I keep going. This is my podcast, Teaming with Microbes, and we talk about gardening and farming and science stuff. It's a little thick, maybe a little, but it's always fun. And I think you folks would really appreciate it. So every Friday, a new one drops, and you can get them anywhere you get podcasts.
Perfect. Perfect. So we put that up there. That's really, really great. To the audience, you have been absolutely wonderful. I've been watching the numbers. We've been looking at, we've been up in the high 70s and toggling around 69, 70s, almost 80s. You guys are fantastic. Thank you. I hope that you've all got some good value, and I hope that you're going to wake up tomorrow morning and start composting and composting and composting some more.
Absolutely. Absolutely. Thank you so much for having me. It's been a pleasure, and we'll do this again someday.
Wonderful. Absolutely. It's been our honor to have you here. Thank you. And goodbye, everybody. Thank you, Team iCow, all the backstopping that you've been doing. Thank you all. And thank you to the audience. Bye-bye.
All right.